Hey class, here we go. Shortest lesson of the unit. We are working with gravitational potential energy. So, gravitational potential energy, or EPG, as we abbreviate it, is all having to do with gravity, obviously, and the height of an object. So, as we lift up an object and it is given height, we are providing it with the ability to do work on whatever is below it. And that work will be due to the force of gravity, right? Fg. And the distance will be the height, right? So the force, as we lift something up, acting on stuff beneath it, is the force of gravity. And the distance is the height, where we can break the force of gravity into its mass times the gravitational constant, right? Mass in kilograms, magnitude of gravity or gravitational constant. Acceleration due to gravity is another way we think about it. Meters per second squared, or newtons per kilogram. So it's important to know that this is magnitude because we're not going to call it a negative direction here. It's on a different reference system than we were looking at with our Unit 3 force of gravity, because positive energy means that it's moving something, it's acting in the same direction as the movement or the distance, whereas negative means it's resisting that motion. And finally, we got height, the distance that our force of gravity is acting over, measured in meters. So this is a nice simple lesson. Most complicated part is this idea of a reference height. So we can change our reference height just like we can change our reference system. And our reference height is where we're going to call this starting height, height of 0. So if an object is above reference height h is positive, then it's above, right? And we have positive potential, gravitational energy. But if it's below that reference height, now we have a negative height, so a negative potential, right? So we can change this h to be positive or negative depending on whether we're above or below our reference point, our reference height. All right, let's look at our first example. We have an object initially at a height of 64 centimeters, and we're going to gain or give it 800 millijoules, right? Lowercase m. So milli means times 10 to the negative 3. You can look on your formula sheet for that. So we have an object, I'll just think of it as a box, with 0.35 kilograms, right? Converting to our standard unit there rather than 350 grams. It is initially at a height of 64 centimeters, and then it gains potential gravitational energy. We want to determine its final height. So if it's gaining, that means we're going to be starting at a reference height, let's say of 0, and we're going to be gaining some height. That's what we're looking for, final height. And we know that the energy that it's gaining is equal to 800 millijoules. So if it gains 800 millijoules of potential gravitational energy, then our change in potential gravitational energy is equal to positive 800 millijoules. Right? It's gaining, not losing potential energy, so we have a positive. All right, we have this change in EPG, gravitational potential energy, which, because we know what that delta sign means, our change, starts with final, EPGF, lots of little subscript there, minus our initial EPGI. So we're going to rearrange this to solve for our final. So our final gravitational potential energy is equal to the change in gravitational potential energy, and we're going to add our initial. Since I started with a reference height of 0 and EPGI is equal to mghi, where hi is 0, we get 0 starting gravitational potential energy. So our EPGF is equal to 0.8 joules. Converting from millijoules to joules, we have to move the decimal place over 3 spots from 800. 1, 2, 3, 0.8 joules. And we're going to add to it. Oh, never mind about this. Please ignore. We're not starting at a height of 0. We're starting at a height of 64 centimeters. So we're going to add this 0.8 joules to our starting mgh, which is 0.35 kilograms, 9.81 meters per second squared gravitational acceleration, and a height of 64 centimeters, which we're going to convert to meters, 0.64 meters. And we get a final gravitational potential energy of 2.997 joules. That's not what the question asks, though. We want to determine its final height. So from EPGF, we have the mass, gravity, and its final height. That's what we're looking for. We're going to rearrange it by dividing mg from both sides. So we have 2.997 joules divided by our mass and our gravity, 9.81. So its final height should be higher than 64 centimeters, we know, and it comes out at 0.873 meters or 87.3 centimeters. And that is the final height of this object that's been lifted up and has a gain in potential energy. All right, next one, we've got some carts rolling down a slope. We know, or essentially the question's telling us that we should know that we have 0 gravitational potential energy at this starting position. In order for that to happen, we need to have 0 height, because this cart does weigh something and it is feeling the force of gravity. So in order for us to have potential gravitational energy of 0, EPGA is equal to 0, we need to have our reference height of 0. So make our reference height the height of the cart at A. Make reference height H0 at position of A. So EPGA is equal to 0, which is what the question is telling us. So it's going to move at a constant speed throughout. We're going to determine the total mechanical energy at B, which is down here. B. From A to B, we have a height difference of, well, the height they gave us is 80 centimeters. We're going down from our reference height, so the height of B is negative 80 centimeters because we're below our reference height. So everything above it would be positive, but everything below it is negative. Since B is below A, we have a negative height of 80 centimeters. So here we're getting into this idea of total mechanical energy. From our last lesson, we know that mechanical energy is the combination of kinetic and potential gravitational. So we're going to need to use the speed of this guy to find its kinetic energy. So our VI, or actually it's a constant velocity, so our speed is 11.2 kilometers per hour given in the question. We're going to convert that to meters per second by dividing by 3.6, and we get 3.11 meters per second. The mechanical energy mechanical of B is equal to the kinetic energy at B plus our gravitational potential energy at B. All right, so kinetic energy is half of mass times speed squared, and our potential gravitational energy is our mass, gravity, and height of B. Let's throw in our numbers. We have half of our mass of 0.25. That's given here. 250 grams or 0.25 kilograms. Kind of a tricky spot to find that on the question, but it is given. And our velocity of 3.11 meters per second. We're going to square that. So we get kilogram meter squared per second squared, or a joule. Good. And we're going to add to it the mass, gravity, and our height, which we determined to be negative because it's below our starting reference. So that's going to be negative 80, or sorry, negative 0.8 meters. 80 centimeters becomes 0.8 meters. And this actually comes out as negative 0.75 joules. So the mechanical energy at B is negative because we're losing our potential gravitational energy, and we're not gaining any kinetic energy because we're at a constant speed. A little bit weird. That question is really focusing in on this idea of our reference height and choosing a reference height to match up to the question, right? It'd be more common to say that our reference height is here and we're starting with a positive potential gravitational energy at A and ending with 0 gravitational potential energy. But hey, the question can ask you a bunch of weird things, and we'll have to adjust our reference height accordingly. So I believe that's it for this week. Good luck with the homework. We had one long lesson, 2 shorter lessons. We're going to have to keep this 3 lessons a week up if we're going to finish the course. So I apologize if that's a lot of work. Best of luck to you. Use me as a resource. I can't wait to hear from you and help you however I can. All right. Thank you, class. I will see you later.